Hey everyone, today we're doing threesome, and threesome is a problem that is medium. And if you understand what twosome is, it should follow what threesome is. But I'm going to read the problem statement out, and I'm going to say it's given an integer array nums. Return all the triplets nums I, nums j, and nums k, such that I is not equal to j, I is not equal to k, and j is not equal to k. So basically, we don't want duplicates. It's going to repeat that here. The solution set must not contain duplicate triplets. Anyways, the target is going to be 0. So while this whole duplicate thing makes the problem a bit of a pain in the ass, the concept is not hard at all. And we should draw on our knowledge of twosome. As you may know, Leetcode is all about pattern recognition. So let's go ahead and try and do twosome first. Now, here is a part where a lot of people trip up because twosome is most commonly taught using the hash map method. In other words, using a dictionary and storing the complement. And this is a very simple and intuitive way to do the problem. It has the benefit of just works and it makes a lot of sense. So why don't we use the dictionary when we want to extrapolate it through threesome? Does the dictionary work? And the answer is not really as well as we want to, because what is the step for us to get from twosome to threesome? In other words, how do we reduce threesome into twosome? Well, let's think about it this way. We have, instead of two numbers, we have three numbers we need to find, and we need to find all possible combinations of three numbers that would sum to our target. But what's one way we can figure it out only using two numbers? Let's say we had twosome just as a function. How could we make this function, how could we use this function to work in our implementation of threesome? Well, what if we thought backwards a little bit? What is a triplet? Well, a triplet is, we have I, J, and K. So we have all these values. Sorry that my handwriting is terrible. And the main thing is that they all sum to 0, right? Now, that means that let's say we move nums I to the other side, we can also state that nums j plus nums k is equal to negative nums I. This intuition does not take a lot of math to understand. It's very basic math. If all these are supposed to sum to 0, our target, then the sum of two of them should equal to 0 minus that target. And if we find all the, not sure what to call them, I guess duplets. If we find all these duplets that sum to this number, then we've actually reduced the problem into twosome, because we can just go ahead and add nums I duplet 1, nums I duplet 2, and remember each duplet is just a j and a k. We can just use all of these, and these are the threesomes. And if we do it for every possible I, then we've solved threesome. So basically, to state it in more simple terms, threesome is twosome for all targets 0 minus nums of I and for all I in nums. Now, why does the dictionary approach not work? And let's go ahead and go down here. So the dictionary approach takes a lot of memory. It only takes O(n) of time to run, but it also takes O(n) memory. So you can see how if we're doing O(n) memory for each element in nums, that would be of n squared memory. And this can get out of hand really fast. And we don't want that because memory in general is not very scalable, right? When you have a lot of elements, it's easier to then default to runtime because then memory will become your bottleneck. So to avoid having to make a dictionary for every single element and store all those dictionaries together, it just becomes very, very convoluted. What we can do instead is go to another method of toSum. This is the toSum dictionary. We'll go to another method of toSum that is slower but uses less memory. toSum pointer or sliding window. And this actually does not take any memory. It just uses the original array. It's going to take n log n runtime, right, to do this toSum because we're going to have to sort the array. But you'll see why that is in a second. I'll walk through an example for toSum. And it takes of constant memory. So you can see how this can help us reduce the amount of memory we're using when we are running through this algorithm in 3Sum. Let me clarify that this is the runtime and this is the memory. So let's go ahead and run through it. So imagine that your array is sorted and you want to find all the duplets that sum to 0. Well, we have our array here and we have our target, which is 0. So how do we consider all the pairs that might sum to 0? Well, general theme in sliding window is that you start at the ends and you move inwards. This works a lot with sorted arrays, and I'll show you why that is, the intuition for that in a second. But the idea is that if your array goes to some crazy negative number, right? And it's sorted, of course, and there is some huge positive number, let's just say 9874. If there's something that sums to 0, there's going to be one on this side and this side of 0, because a negative number and a positive number, the only way two numbers can sum to 0 is if one is positive and one is negative. So we start from the left and we start from the right in order to find those possible pairs. Now, they could not exist. For example, let's say we had the array -2 and 1. Just because there's a positive number and a negative number does not mean that these sum to 0. But if there is a pair that sums to 0, one has to be negative and one has to be positive. And a very intuitive way to search for that is to start at the ends, because our array is sorted and this side will be positive, the right side will be positive, and the left side will start with the negatives. And if you follow this intuition, then you can extrapolate for numbers that are not 0, targets that are not 0. If there is a sum that adds to that target, then one will be on the left side and one will be on the right side of the array. And you can find that possible pairing by moving through the array with your pointers. But let's go ahead and run through our little trivial example here. So our left pointer is going to be pointing at -1 and our right pointer is going to be pointing at 1. So -1 plus 1, what does that equal? It's equal to 0. So clearly that means that we found a solution. So -1 and 1 is a possible pair. So what else should we do now? Well, we should move both our left and right pointers because we don't want duplicates. We don't want to consider this -1 and this 1 again. And then we move them both into the middle. So we move them both into the middle. And now they're both pointing at the same thing. And obviously, we don't want to add 0, 0 because that is not a duplicate. That is just one element being repeated twice. So an important thing we have to watch out for is that L should always be less than R. This has to be true. We have to make sure that L is less than R when we're doing the sliding window method, because if they're pointing at the same element, that means that we should end our loop. So that's the basic idea. Now let's consider a little bit of a more complicated array. So how do we adjust our left and right pointers in this case? Well, of course, we start at the ends of the array, and let me move this so it's out of frame. So of course, we start at the ends of the array like we did before, but now we see that -2 and 3 are equal to 1. So if our target is 0, right, this is not a valid pair. So how should we adjust our pointers so that we consider a valid pair? Well, the concept is when our current sum is greater than our target, we should try to adjust our pointer so that it gets closer to 0. And one way of doing that is moving R, right? Because R is currently pointing at a larger element. Why don't we move R so that's pointing at a smaller element? So instead of having R pointing here, now R can point to here. And you can see that this will reduce our sum to equal to 0. So we have indeed found something that adds to 0. We found a two-sum or a duplet, whatever you want to call it. We found one. So this will be added to our answer. Our answer is now going to have -2 and 2 in it. If we do that same thing where we move both L's to the, if we both move both pointers to the middle, now they're going to both be pointing at -1, and we know that our our two-sum is now done. So we adjust our pointers based on the sum in order to consider all possible pairs that might add to our target. In this case, that meant adjusting our right pointer by 1 to get our desired result. That's how you do two-sum with the two-pointer method. How do we extrapolate this to three-sum? Well, like we said before, there is a way to just run two-sum on all the complements that are possible in this given array. We're going to sort it first because we need to do that for our two-pointer solution. And how are we going to get the three-sum of this? Well, remember, if we run two-sum n times for each target minus nums I for I in nums, we'll get all the triplets we need. So if we partition the array, let's say this is I, this is the starting, we just need to find all the duplets here, or all the pairs here, that sum to 0 minus -4, which is equal to 4. As long as A plus B is equal to 4, this means that 4 plus A plus B will equal 0. So we just run our two-sum on this array. So run two-sum on -1, -1, 0. Let me do a shorthand here, right? Run two-sum on this blue square, this blue box, until we have for the target equal to 4. That's how we'll find the triplets. And you can see here that there aren't going to be any triplets that include -4. What do we do next? So we saw that there were no triplets that include -4. So what is our new element that we need to consider the complements for? Well, the next one would be -1. And what should we run two-sum on? Well, we should run two-sum on the rest of this array here, the remainder part of the array. And what is our target? Well, our target should be whatever 0 minus -1 is, which is 1. So our new target is 1. This is our target. And let me do that for you really quickly. If our left pointer is here and our right pointer is here, well, we can see that -1 plus 2 is equal to 1. So we found a good triplet. We found a triplet that adds to 0. That triplet is -1 as well as -1 and 2 are L and R. So that's how we do it. And we can move L and R again. So now they point here, and you can see that now 0 plus 1 is also equal to 1. So we've found yet another triplet. So you can see how we're finding these triplets, right? Now we have that same -1, and this time we have 0 and 1. And you can see that the sum here is in fact 0. So now L and R, we're going to subtract so L has crossed R, and we'll see that our loop can no longer continue. But that's the general idea. It's going to take a while to really understand this, but as long as you get this part, you have basically solved the question. Now, if you solve just for this, you're going to get duplicates, but I will go ahead and just show you how this works. Like we said, we're going to reduce 3-sum to 2-sum. So let's just go ahead and forget that the problem is 3-sum and just write 2-sum using the sliding window method. So let's just say our target is equal to 0. Okay, this is arbitrary. I'm just going to choose 0, and you'll see that we'll change this later because, you know, this is not the problem. But for our purposes, we'll just say the target is 0. And we're going to say that L is equal to 0. L is going to point to the first element, and R is going to point to the last element. And these are indices. So L and R are indices. We're going to have L be the left side of the window, R be the right side of the window, and we're going to slide them in order to find the elements of those pairs that are going to add up to 0. And what do we do here? Well, while L is less than R, remember, we don't want our edges of the window to slide into each other, over each other. We're going to say that if nums L plus nums R is equal to our target, then we've found a good pair. So we need to keep track of our answers, right? Our pairs. So let's have a array to do that, and we'll go ahead and append L and R to that array. And let's say that the sum, so m nums L plus nums R, is less than the target. Well, what should we do? Well, we should adjust our L pointer to be greater, because remember, our array is sorted. Now, did we ever sort that array? No, so we should go ahead and do that. So let's go ahead and sort our array to begin with. That's very easy to do in Python. Now that we've done that, you can see that our sum is less than target. So we have to increase our L in order to make sure that we are now considering a bigger element at L. Like, for example, in this array, it's already sorted. You can see, like, obviously, if our target was 2 hypothetically, and we're considering 0 and 1, we would want our L to move over here, because 0 and 1 only sum to 1. We want our target to be 2. So we need to make sure our L is moving to consider something that might be a possible pair. So let's do that. And else, well, you already know, R is going to move as well. And it's important when we find a pair that reaches our target that we also move our window to no longer include those elements, because we need to progress. We can't just consider the same elements over and over again. We want to make sure our window is always moving and that our problem size is always becoming smaller. So let's go ahead and just run this. Notice that we did not solve the problem, but this is a 2-sum implementation. So let's see if it's doing a 2-sum here. Actually, I don't think it is. Oh, because I never returned answer. So return answer. So you can see here So the question actually doesn't ask for the indices, it asks for the elements. So we can go ahead and fix that really quickly here. So remember, I'm not trying to solve 3-sum here, I'm just trying to solve 2-sum. So yeah, you can see here that we're finding these pairs, and we're finding these pairs here, we're finding these pairs here, and yeah, this implementation seems to work for 2-sum. Now, let's make this 3-sum. And remember the magic step. We're just going to consider all the complements for every n in nums. Like I said, we have to consider each complement in the array. So let's go ahead and do this. So now we have I. So our target is going to be 0 minus nums I, because this is the complement that we are looking for. This is the target we're going to be looking for. And instead of our pairs here, we're going to make triplets. So it's going to be the element at I. That's going to be our answer. And instead of L being 0 every time, L is going to be I plus 1. I'm going to tell you ahead of time that it's not going to pass every case, but let's see if it passes any cases. Yeah, and you can see it's passing case 2, and it's passing case 3, it's failing case 4, and it's failing case 1. What is the problem with 4 and 1? Well, if we look at our output, you can see that we're still getting duplicates. Now, here is something you should do in an interview if you don't know how you can fix this problem. Well, you can do a little trick if you know something about data structures, and you can just have our answer be a set. And a set gets rid of duplicates automatically for you. So what you can go ahead and do is append, instead of a array, you can append a tuple, which you can put in a set because set has to have immutable elements. So if we go ahead and do something like this, it doesn't have append, so you have to do like add, I think. And yeah, it will actually work. But this is actually not the most efficient way, although I don't believe it actually changes the runtime like dramatically. Although checking for membership in a set, checking if a set is still valid, essentially that there are no duplicates, might be the reason why it's taking so long. You've technically solved the problem in a clever way, but instead of using a set, the actual way to do it is to instead consider what we're doing here, right? When we append this. So we've already avoided duplicates in a way by moving our L pointer to I plus 1 instead of repeating from 0 all the time. But there's also something that we should consider here too. If, for example, let's go ahead and use one of those test cases we're failing here. Let's go ahead and consider this example, which is obviously creating duplicates. Now, why is it doing that? So first, our I is going to be here, and then our L is going to be here, and our R is going to be here. So obviously, what is our target? Well, our target is going to be 2, because 2 plus negative 2 will equal to 0. So we obviously have that right off the bat. What do we have? We have negative 2, which is this. We have 0 and 2. So this is a valid triplet. So what do? We move L and R, and now L and R point here, and you can see our obvious problem because this is also 0 and 2. So it's the same triplet and it's also valid, but that causes a problem. And let me use red here to kind of show you exactly what is the problem. This L and R is this 0 and 2, but there's also an L and R that's this 0 and 2. So how do we avoid that? Well, there's a little trick, is that when you find an answer, you don't want to consider any other answer that has the same element as its L, because that's how you get duplicates. This other 0 existing being the same as this 0 is how we got duplicates. So if we just go ahead and check that every time we get this answer, when we do those movements, we need to consider if L is the same as the L that it was before. And we can just do that by checking that nums of L is equal to nums of L minus 1. And if they are equal, that means that we might make a duplicate. So we don't want to proceed. We want to instead move L to the. So make L equal to L plus 1 until nums of L is not equal to nums of L plus 1. So remember, we have moved our L and R. Now it's time to see if nums of L is equal to nums of L minus 1. This means that our element is the same as the one preceding it. If it is, then let's go ahead and move L. And we don't want to do this just once. We want to do it as long as it is true. So let's go ahead and do this. And now we have avoided this problem. It should be fixed now. So let's go ahead and run this. And let's make sure L is less than R, because L can definitely increase too much. And there's also just another stupid case where you might have duplicate triplets just based on there being duplicate elements. And this is also extremely unfortunate. I'm going to go ahead and run here. And you can see that we're still failing case 1. And I'm going to go ahead and make, So case 1 is failing because if we go ahead and sort this array, so -1, -4, -1, 0, 1, 2. Why is it failing? So we're going to consider L being here, R being here. Target, once again, is 1. So -1 plus 2 is equal to 1. So we have our good triplet. -1, -1, and 2. This is red and this is blue. These blue ones, these red ones. Now, what do we do in that circumstance? Well, we move our pointers. So let's go ahead and move them. Now it's pointing here and R is pointing here. And yes, 0 plus 1 does equal to 1. So now we have 0 and 1. So we found the triplets. The problem is when we use this element as our I, in this case, I is equal to 2. When this element is our I, then we're going to get the exact same triplets. We're going to get, once again, -1, -1, and 2. Or excuse me, we won't get -1, -1, and 2, but we will get -1, 1, and 2. We're going to get a duplicate of this because let's see, if we run through this, right, let me just prove that really trivially. So once again, our R is pointing at here. It's not going to, 0 plus 2 is not equal to 1. So now, if we move R to the left, we are once again going to get -1, 0, 0, 0, and 1. You can see that these two look the same, but they use different -1s. And thanks to that, they become duplicates. Let's use a more different color. This -1 is from this, but it doesn't matter because the result is a duplicate, and we do not want duplicates. So how do we prevent this? Well, we do the same thing. We shift our I if we see that is equal to the past I. So when we're here, right, when our I is here, we check, is it equal to the past I? If it was, then we move forward. And we'll just consider I as being 0. So that's how we get around this little caveat. Okay, back to code. Let's go ahead and implement that really quickly. So when we consider the I if nums I is equal to nums I minus 1, then we'll continue. We don't want to consider it, excuse me, because all we're going to make is duplicates. Let's go ahead and run now. It's failing. So one little caveat once again, and this is really annoying, but you can see here that let's say I is 0, nums 0 minus 1 is nums negative 1, and it's calculating that 0 is equal to 0 here. So obviously we don't want to use the wraparound array, like stupid thing of Python. So I'm going to make sure that I is not equal to 0. Okay, in fact, we can, yeah, now it should be fine. And yeah, you can see we now pass that case because it's no longer comparing nums negative 1 and nums 0. So that's just a little stupid Python thing that you have to account for. But, you know, it's not even a Python thing. It's just important to always be aware of what your indices are, because if you're indexing outside the array or if you're indexing somewhere you don't expect, it could cause problems. So let's go ahead and submit and see if we finally covered all the edge cases. And we've covered all the edge cases. Now, if you cannot come up with these edge cases in an interview, remember that you can always use the set solution to kind of wiggle your way out of that one. And yeah, this is an annoying problem with some caveats due to the not wanting duplicates rule. But if you just think logically, you should be able to get around those exceptions. And really the base logic is not that much more complicated than two-sum. You're just doing two-sum n times for each element and each possible complement. And this can be extrapolated to 4-sum, to 5-sum, to n-sum, however many elements you want in your little arrays, you can come up with a solution. So yeah, that's it for this video.